So let's go through polymerizations. We have additions polymerizations. Of course, the other type of polymerization is condensation polymerization. So addition polymerization, it starts from monomer with double bonds. So for example, alkene. So alkene is the one with double bonds. So when alkenes is going to join up to form polymer, so the double bond will change to single bond. Okay, so it's something like this. For example, I draw it out at the side here. So it has double bond. Then they want to join up with another alkene. So basically what happens is they will form polymer. You see the double bond here. This part, the double bond becomes single bond. Then they form new bond. They form new bond with others. So I put it in blue color. And then the monomer at the side is connected. Okay, so this is how they form polymer. From a double bond monomer become single bond, and the single bond is, of course, the polymer. So if you don't want to draw in that way, so there is another alternative here. So we can draw in this way. Okay, so this is another way to represent the polymer. Okay, so and for the reactant also, if you don't want to draw monomer plus monomer, you can also draw. Okay, you can also draw like this. So let's say I pull it this way. Okay, so we can also draw N of the alkene change to polymer. So this is another way. The first way, and this is the second way. So the second way is easier. Now let's move on. Monomer are alkenes. Polymer form is polyalkene. Polyalkene. So let's say, for example, this case, ethene. Ethene. So after they form polymer, we call it polyethylene. So this is the structures, polyethylene. So next point, alkene joins to itself. No molecules lost. You know, they are just changing double bond to single bond and then they join up. So they don't eliminate anything. So that is the difference from the condensations polymerization where they remove water or they remove HCl. This addition polymerization, it doesn't remove any molecules. Okay, so next point, molecular mass of polymer is multiple of monomer. It's multiple of monomer. So should be reasonable, you know. So let's say, for example, you see, you use N of this alkene, and then they will form a polymer with length N. So the molecular mass is just N multiply N times of this relative mass of the monomer. Okay. Now, physical properties of polymers. Only carbon and hydrogen presence. That means only when the Waugh forces presence. So they are trying to say that no hydrogen bonds. Okay. So when the Waugh, which is quite weak, you know. So the induced dipole is there. So presence of chlorine or fluorine will make the polymers having dipoles. That means have delta negative and delta positive. So that we have permanent dipole interactions. So they are trying to say that if it is just a polymer without chlorine, fluorine, so it's just carbon, hydrogen alone, then the polymer will have temporarily dipole, induced dipole. But with the presence of chlorine or fluorine in the polymer, for example, this case, fluorine is there in the polymer, then they will have temporary dipole, induced dipole, as well as permanent dipole. They have permanent dipole also. Okay. So this one have permanent dipole and temporary dipole, induced dipole. But this one, it has temporarily dipole, induced dipole only. Okay. Now next one, longer chains with fewer side chain has stronger van der Waals forces. Okay, so that means if they have less side chain, then they are straight. Their structures is more straight. So imagine something like this. If the polymer has no side chain, so it looks like a long structure then. And together with another polymer with long structures like this, so of course the van der Waals forces is stronger because they can form van der Waals forces everywhere along the polymer, and hence it is stronger. But if there are side change, so this is no branch. So if they have many branches, so then the polymer looks like more spherical, and then together with another polymer which is more spherical, so basically they can form less van der Waals forces because of the surface area in contact is getting lesser. So then the van der Waals forces is weaker for this case because they can form not too many van der Waals forces. Compared to this one, they can form a lot of van der Waals forces when there is no branch. Okay, so it affects in terms of the melting point and boiling point when there is no branch and many branches. So you should expect when there is no branch, the melting point and the boiling point should be higher. And when there are branches, so the melting point, boiling point should be lower. Okay, should be lower. Okay, now let's see next part. So this one, ethene, you join up, they form polyethylene. So polyethylene is plastic. It's plastic. So this is plastic. Polytetrafluoroethene. So imagine initially they are like, when they are monomer, they are like this. Double bond with F, 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 F. Okay, so there are 4 fluorine around the 2 carbon with double bond. So that's why this is called tetrafluoroethene. Tetrafluoroethene. Tetra means 4, and then fluoro means fluorine, ethene means 2 carbon. So when they join up, they form a polymer where the double bond, as you can see easily, the double bond becomes single bond. So polytetrafluoroethene, where can we see this polymer? This is seen in Teflon. So what is Teflon? Teflon is actually the non-stick layer of the pan. So it's a black color layer which makes the pan non-stick. So Teflon. Okay. Now in this table we can see 2 columns. So the left hand side is LDPE, low density polyethylene. Low density. So this is low density polyethylene. Low density polyethylene. It is soft plastic. Soft plastic. For example, our plastic bag. Is soft plastic. Okay, so made with non-polar polymer. Non-polar polymer. So, for example, this one, only carbon hydrogens present and then there are non-polar. Highly branched chains, so there are this type. Okay, so highly branched chain. So I write here, example, LDPE, highly branched chain. Because of highly branched chains, it has less van der Waals forces that can form between one sphere with another sphere. And because less van der Waals forces, or less temporary dipole-induced dipole, so it make less temporary dipole-induced dipole, it makes the polymer has low melting point. So imagine a plastic bag has low melting point, so you can easily burn then it melts. So chain cannot pack closely due to random branching, leaving gaps. So imagine you have sphere here, and then another sphere over here. So another sphere maybe here. Okay, so there are gap. There are many gaps in between. So because of the gaps, it makes the plastic has low density. So it is very light. Imagine plastic bag. Plastic bag is very light. So that is LDPE. Okay. Then next one, HDPE. So should be able to predict this is high density polyethylene. So what they mention here, use Jagger catalyst. So how about this one? Do we need to use Jagger catalyst? Actually, no need. So with catalyst, what happens is they can form a more specific structures. Without catalyst, maybe the structures is quite random. Okay, with catalyst, more special structures can be formed. Specific structures can be formed. Then hard plastic made with non-polar polymer. So they can form hard plastic. So this is soft plastic. This is hard plastic. So for example, soft plastic is plastic bag, right? So hard plastic, maybe the pail. The pail is hard plastic. Okay, so unbranched chains. So it belongs to this situation. Unbranched. They are straight polymer. Okay, so I can label it here. This one example is HDPE. And then next one, unbranched chains, high melting point. Okay, so why high melting point? Because of this, they can form a lot of temporarily dipole-induced dipole, and because of that, they have high melting point. Closely packed chains, closely packed and less gaps. So imagine they are straight line, they are straight polymer. So you can just put them close together easily, so you can just press them and they are close together and leaving no gaps, and hence it has high density and it is heavier compared to a plastic bag. Okay, so let's move on. The other side. 12.2, natural and synthetic rubber. Okay, so just now we learned about plastic, so now we learn about rubber. So yeah, rubber is formed naturally and synthetically by additions polymers. So again, this is additions polymerization. So you should expect some double bond at the beginning, but it is a bit special. So you see natural rubber, the monomer is called isoprene. Typo error here. Isoprene. Okay. So you can see the double bond is over here and here. And what happened is during the polymerization reaction, the middle one will become a double bond. Okay, the middle one will become a double bond. And then the double bond at the side will become single bond. Okay, we become single bond. So you should expect something like this happen. The bonding electron, one of the bonding electron goes sideways to form a new single bond. Another bonding electron come to the middle. So likewise here also come to the middle to form a new double bond in the middle. So the other electron from the double bond will go sideways to form single bond. So basically they form polymer in that way. Okay, the double bond go to the middle because of the moving of the electrons from the side to the middle. Likewise here from the side to the middle, and from the side also one of the electron go out to extend another single bond with another monomer. So likewise here also. So they form natural rubber, and natural rubber, right? They are soft, they are soft. So we had to do vulcanizations to make it stronger. So process makes rubber more resilient and harder, links rubber polymer chain by covalent bond across sulfur bridges. So you can see, initially natural rubber, right, is just a straight chain, and then because of that it is not strong. So vulcanization is where we add the sulfur bridge in this way to join one polymer with another polymer. So you can put it at many points to form the disulfide disulfide bridge. Okay, so basically they can add one extra bond there because there is a double bond there lah. So this double bond make the disulfide bridge able to form. Okay, now let's move on. Synthetic rubber. So synthetic rubber means man-made rubber. Okay, so we do it in the factory, for example, So not like natural rubber, we get it from the rubber tree. Okay, so this one, synthetic rubber. Now, let's compare the structures. Just now isoprene, you can see the structures is just carbon hydrogens only. But this one, there is a chlorine over here. Chlorine over here. Compared to this is CH3 over there, and this is chlorine over here. So this part, the backbone here, looks the same with this one. It looks the same. So where we have double bond, single bond, and double bond. And how the electron move? Same with this one also. Two electrons from the side to the middle. So the side double bond shift to the middle. And the electron also goes sideways to form new single covalent bond with others. So likewise here, form new single covalent bond with others. Okay. Then they join up. When they join up, we call it synthetic rubber, or the polymer is also known as neoprene. So chloroprene become neoprene. Okay. So synthetic rubber is basically a stronger rubber. So now, next one, condensations polymerizations. So the word condensation means you should think of water. Water will be eliminated as one of the product. So they will form polymer as well as water. But it is not just water, it can be HCl also. So you can see the point here. When two different molecules, monomers, different molecules or different monomers react together to form an ester or amide bond with the elimination of a small molecule like H2O or HCl. Okay, so what is ester again? Ester is C double bond O and O. This is ester. Amide is C double bond O followed by NH. This is amide. Okay, so a quick revision on how these bonds are formed. So for example, carboxylic acid react with amine, the NH2. Then they can form amides by removing H2O. Okay. So ester, a quick revision. Ester is formed by alcohol plus carboxylic acid. Where the carboxylic acid remove OH, the alcohol remove H. Then they form ester. So again, with these two examples, you can see they are removing H2O. So in what situations they will remove HCl then? So if it's a sal chloride, so for example like CO, okay, like C double bond O, Cl, this is a sal chloride, react with alcohol. So in this case, they will remove HCl. Okay, so they will remove HCl. Okay, center for this.